Okay, so for our demo, sometimes a function may need more than one formula to accurately model a real-life situation. So for example, taxi fares, right? There might be a flat fee, like even if you only go a block, right? And then in addition to that flat fee, you have to pay so much per mile or something. The US tax code is a piecewise function in that the percent that you are taxed on the amount you make under $3,000, I think, is 0, right? Your first $3,000 you make is not taxed. And then like 3,000 to, I do not know the numbers, but 3,000 to some other amount is taxed at, I'm making them up, let's say 10%, right? And then there's another bracket where you get taxed at a higher rate. And then late fee charges for credit cards. Sometimes those are like the maximum of $10 or 1% of your balance, something like that. So there's two different formulas. And then all of these require more than one formula to model them. So in these situations, we say the function is defined on pieces of the domain, and we call it a piecewise function. So the graph that we just found formulas for up here, we're going to use that graph to represent a piecewise function, and it shows the amount of water in thousands of gallons in a swimming pool after T hours have elapsed. So my x-axis is time, my y-axis is gallons of water in the swimming pool. How has the amount of water in the pool changed over the interval 0 to 50? So from time 0 to time 50, what has happened to the water in the pool? Overall, it lost 2 gallons, yeah. Can you tell me a story about the water in the pool? Yeah. Sure, yeah. They filled it up. It stayed steady for about 10 hours, right? And then maybe the liner broke and then it all spilled out. Yeah, good. So it filled up. And then it was constant for a little while, and then it emptied. All right, so over what interval is the water level in the pool increasing? And for interval, I want just the independent variable of time. Over what times was the water level increasing? 0 to 20, right? So this is my x interval. Over that interval, the amount of water in the pool is going up. So the water level in the pool is increasing from 0 to 20. That's the interval. And then over what interval is the water level constant? 20 to 30. So I'm just going to highlight that underneath here. That's a different piece of the domain where something different is happening. From 20 to 30, it's constant. And then over what time interval is the water decreasing? 30 to 50. So I'm just going to highlight that on the t-axis, 30 to 50. Above that, you can see that the water level is decreasing. So that's 30 to 50. So these three intervals that I wrote over here and highlighted on the axis, they define different pieces of the domain for our piecewise function. Okay, so we have to break this function into 3 different domains. If I wanted to give a formula for this, I would need 3 different formulas, one for each of these 3 different domains. Okay. So we can represent the pool problem by writing the number of gallons in thousands, G for gallons, as a function of the number of hours T using a piecewise function. And this is our standard notation for a piecewise function. You put G of T equals and then one big curly bracket. And I've got 3 different pieces to this function, and I write them so I have 3 different formulas, right? And these are the 3 formulas that we came up with together in the preview exercises, right? So my over my orange interval, the equation of that line was 3/10 t plus 2. Okay, and then over the green interval, my equation was y equals 8. G of t is like my y, right? And then over this blue interval from 30 to 50, my equation was y equals negative 0.4t plus 20. So you list the three different formulas, and then the last piece is to list what domain those formulas apply to. Okay? So the 0.3t plus 2, that applies to the orange domain, which is from 0 to 20. T's from 0 to 20. So you use this formula, 0.3t plus 2, if t is between 0 and 20. You use the 8, so that's the orange domain, right? You use the 8 formula when you're in the green domain, and this is just describing the green domain with an inequality. T is between 20 and 30. Have the formula y equals 8. And then when you use the blue domain, you use that last formula, negative 0.4t plus 20. So what is the blue domain? How do I write it as an inequality? Yep. Perfect. Good, good. So Cassandra is noticing that when do you use the or equal to and when do you use the strictly less than formula? Okay, so let's see. I'm going to write in what I had here. This was 30 less than t less than or equal to 50. Okay, so if there's a closed circle, you typically use an equal to, and if there's an open circle, you typically use a strictly less than. But you can see that like this line and this line share this point, right? It's a closed circle on both of them. So technically, I could put an or equal to here and here. It's just kind of like bad grammar because they're two different formulas. It's possible that if I plugged 20 into this one and 20 into this one, I'd get a different y value. In this case, I don't. But with two different formulas, you could get two different values at that endpoint. And then if I had two different values at that one endpoint, this would not be a function. Yeah. So in this case, it would be fine. You're not violating any rules of functions if you put the or equal to here. It's just kind of, I don't know. It's just like saying, like using a double negative, or like everybody will know it's okay, know what you mean, and it's okay. It's just kind of not done. Convention. So here, and then you just pick one, whichever one you want to include the 20 on. You can include it here or here, but you typically don't include it in both. So here, because it was chosen for you to include the 30 in the middle one, we didn't include the 30 in the next one. Yeah. Right. Or it could be that the function would look something like, imagine instead of this middle piece, maybe it looks like this, right? So you would say 20 to 30, and you definitely would include the 20 in the first one, but not the second one. So, but that would still... Yep, it would still be a piecewise function, even if it's not continuous, meaning you have to pick up your pencil to draw it. Good questions. Okay, so here's another example of a piecewise function. You are on cell phone plan. Okay, so a cell phone plan with Verizon is $79 a month, and you get 700 minutes, and any minutes over 700 gets charged 45 cents a minute. Okay, so if C is your monthly cost and M is the number of minutes you use, we want to figure out the cost for 535 minutes. Okay, so what do you think? What would the cost for 535 minutes be? $79, because you're within your limit of 700. So you just pay your flat fee of 79. So 535 minutes cost $79. Okay. What's the cost for 850 minutes? Say it again. How'd you figure it out? Great. Yeah. So 700 minutes are paid for with your $79, right? So you say, okay, subtract from 850, take away the 700 you already paid for, right? That leaves you with 150 minutes that you still have to pay for. You multiply that by 45 cents per minute, and then you got to add on your base fee, $79, and let's see what that comes out to. 150 times 0.45 plus 79, 146.50. So to interpret it, I would say 850 minutes costs $146.50. All right, so having calculated a couple of different costs, I want to try to use my new piecewise function notation to describe the cost in a formula. Okay, so M is going to be the number of minutes, C of M is the cost. So I've basically got two different formulas, right? What's the easiest of the two formulas? The first one, which is $79, right? So your cost could just be $79. And then I'll put if what? Yep, if M is less than, we'll say or equal to, because I think you actually get 700 minutes. So you can use that 700th one. Yep, so $79 if M is less than or equal to 700. So my other formula would have to be when M is greater than 700, but I'll write that in after. But what is the formula? How do we figure it out? Yep. Look at what we did up here for 850 minutes, but instead of an 850, just use a generic M, right? So you're going to take 0.45 times M minus 700 and add on the $79 base fee. So you have to subtract the 700 because that tells you how many minutes over you went. Then multiply that by 45 cents for each overage minute. Add your base fee of $79, and that's your formula if M is more than 700 minutes. So what do you think? Seem okay? So the notation takes a little bit of practice. Remember, you put C of M equals a big curly bracket to open. Then you list your formulas and when they apply. And there is no close curly bracket. So that's something that kind of throws a lot of people. There's no close curly bracket. Yeah. A different formula? Yeah, absolutely. Yeah, if it's a different slope, then you got to write a whole different formula. Yep. All right, so let's move on to one more example. Here's a formula I've given you, and I want you to draw a graph of it. So if you don't know what a graph looks like, you can always just make an XY chart and plot a bunch of points, right? Okay, so I have two formulas here. I have y equals x squared, and I have y equals 1 minus x. Okay, so those are my two formulas. They apply, I have to apply them in different locations. Okay, so let's work on y equals x squared first. So I'm just going to make a little XY chart, get some points to plot, and see what this graph looks like. All right, so what kind of x values can I plug into the x squared formula? negative, 0, a half, 3/4, 7/8, anything up to 1 but not 1, right? So let's plug in some numbers that make sense for this, like maybe -3, -2, -1, 0. Maybe I'll do a half and 3/4. And I'm going to see where 1 goes, even though it's actually not on the graph, right? So I'm just going to put a little star there because it is the end point of the interval, even though it's not included. All right, so if I take each of these x values and plug into my formula, I just square them. So I'm going to get 9, 4, 1, 0, 1/4, 9/16, 1. And I'll plot them. So let's see, -3, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. -2, 4. -1, 1, 0, 0. And then I get a half, a fourth, 3/4, 9/16, which is a little bigger, and then 1, 1, but that's not included, so I put an open circle. So if I connect those with a nice smooth curve, it just looks like that. And some of you might remember that graph from a previous class, a parabola, right? So there's my picture of y equals x squared only on the domain that I told you to graph it, only for x is smaller than 1. All right, and then let's look at y equals 1 minus x. I'm going to make an xy chart. Now, what kind of x's am I allowed to put in the x column here? 1 and bigger. I actually can put 1 in because it says greater than or equal to 1. So I can put in 1 and anything bigger. So I'll put like 2, 3, and 4. So if I put a 1 in here, I get 0. If I put in a 2, I get -1. 1 minus 3 is -2. 1 minus 4 is -3. So I can plot these. I get 1, 0 right here. 2, -1. 3, -2. 4, -3. And this is quite clearly a line. So just connect those. And that is a graph of my piecewise function. Is that function continuous? No. Continuous means that you can draw the whole thing without picking up your pencil. Is it continuous? Nope. Nope. Yeah, there's a jump right here that makes it not continuous. Okay. But is it a function? Yeah, it definitely passes the vertical line test. This spot right here would be the only place I'd have to be worried about, but because I have an open here and a closed here, it passes. Okay, so it is a function. Okay, so I have 4 examples, I think. They get progressively harder, and I just want you to know that if you get to the very last one, it's pretty hard. So like work at it, but if you don't finish it by the end of class, like don't sink a lot of time into trying to get this one done, right? It obviously has to do with taxes, which would make it very complicated, right?